it's very, very difficult to get together even with 2 or 3 colleagues. So to get a whole room full like this is really special. So many, many thanks for making the effort to be here today. So I'm Douglas Guys. I'm Katie's supervisor, and be introducing her today. Most of you know her very, very well. Just before I do, I just wanted to extend a special welcome to Katie's family for coming today and supporting her and being here. That's really, really special for us, and her many friends here as well. We'll be joined a little bit later. We had some technical issues by 2 other special guests, Gail Schaefer and Dan Huber, who are both on the committee, together with Vadim, Fabian, and Russell. And they'll be connecting from Mount Wilson Observatory, where it's 3 hours earlier, and they're setting up to do a Skype session, so we'll have them as part of this as well in just a few minutes. So Katie's had a very impressive scholastic career to get to this place today. She got her bachelor's in 2005 at Guilford College, a wonderful liberal arts college in Greensboro, North Carolina. And she got a master's degree at the University of Arkansas in 2007. And then many of you may not know, she taught physics as a lecturer for 4 years at the Coastal Carolina University in Conway, South Carolina. Thank you. Come on in. And she arrived here at Georgia State University in 2011, and she has worked with me pretty much ever since her arrival. I think she took stellar hemispheres and then decided that it would be worthwhile to get going on some interesting problems in stellar astronomy. And so she's been working with me since then. And she's been one of the pioneers who've really seen what could be done with our char array interferometer out in California to really start looking at the fundamental properties of stars through measuring their angular diameters. And I still call her one of the pioneers because, as you'll see today, she has really pushed this into an area that's never been done before in terms of very, very tiny stars, apparently tiny stars in the sky. And it's been very, very difficult and challenging work, and she's done extremely well with that. So she follows in the footsteps of at least 3 other grad students who've worked on angular diameters with the array: Ellen Baines, Tabitha Boyajian, and Jeremy Jones, who worked on the A stars. And as you'll learn today, Katie has extended this in the sense of going to hotter stars, the more massive stars, which are usually very, very far away and therefore very, very tiny. So it's been extremely difficult work, but she's excelled at it. She's going to report on today. I don't want to steal your thunder, but one of the smallest objects she's looking at is 0.12 milliarc seconds. And just to get an idea of that, it's about the size of the frisbee on the surface of the moon. So if you could imagine how tiny that is in the sky, that's the kind of thing that she's been able to measure. So it's absolutely phenomenal work. She's accomplished a huge amount here as a colleague and supporting our community of physics and astronomers. She acted as our Hard Labor Creek Observatory Fellow for a number of years and was involved with setting up the schedule and helping make sure that things ran okay for our open house nights out at Hard Labor Creek. So we're grateful for that activity and what she's done. So she's had a very, very central role as part of our community here. So I'm grateful to you for everything you've done, and thank you for being such a great colleague. So today she's going to be talking about fundamental properties of the very hot O and B stars from optical interferometry. Thanks.
Great. All right, thank you, Doug, for that wonderful introduction. So today I'll be talking about my dissertation research, as Doug said, the fundamental properties of O and B stars with optical interferometry. I just want to start off with this picture. This is actually one of the stars in my sample that I studied. This is Zeta Oph, and it's a runaway star. And so this is the bow shock that it's creating as it moves to the interstellar medium. So I thought it was a really neat picture since it was one of my stars. So I just want to start off thanking a few people. Of course, thanks to Doug for being an amazing advisor, and thank you to all my committee members for taking the time to read my dissertation. We've got Doug, Russell, Fabian, and Vadim are here today, and then, as Doug said, we have Gail and Dan joining us from Mount Wilson on Skype. And then a big thank you to all the members of the CHARA team, from those involved in getting it built and running to keeping it running every day, all of the night operators that make nightly observations possible. Of course, I couldn't have done any of this research without them. And I really want to give a big thanks to Gail and Dan. Gail helped me with pretty much anything interferometry or CHARA related, so it really taught me a lot of things. And Dan taught me how to use the Pavo reduction software. Big thanks to all my fellow grad students for keeping me sane, especially Michelle, Crystal, and Ryan. And thank you to my husband and my family for being here today. So a quick rundown of what I'll talk about. First, I'll give an introduction to what O and B stars are in the first place. Talk about my observational sample, my observational methods, so using the char array, talk a little bit about interferometry. My modeling methods, I did some modeling with spectrophotometry to go with my interferometric measurements. And then finally get to some results on the O stars, the B stars, and discussion of those results. So to start off, we have our HR diagram, or Hertzsprung-Russell diagram, that we all know and love, that we use to classify different types of stars. So we have temperature increasing to the left on the horizontal axis. Also on the horizontal axis is the letters that indicate spectral type. So spectral type is associated with temperature of the star. So O and B, when I say O and B stars, that means it's a certain type of star, has a certain temperature and a certain mass. And then we have luminosity on the vertical axis. So B stars will lay around here on the main sequence. So they have a mass range of 3 to 16 solar masses, 10 to 30,000 Kelvin, and they have a fairly short lifetime of 9 to 150 billion years. This is because they are so massive and luminous, they burn through their fuel a lot more quickly than less massive stars, so they have a lot shorter lifetimes. And then even farther up on the main sequence towards the corner, we have the O stars, which are even more massive and more luminous. They have a range of 16 to 200 solar masses, a hotter temperature range of 30 to 55,000 Kelvin. For reference, the surface of the sun is about 5,800 Kelvin. So these are much, much hotter than the sun. And they have an even shorter lifetime of 3 to 30 million years because they're even more massive than B stars, so they burn through their fuel even more quickly. So the spectral energy distribution, or SED, shortened version of it, for O and B stars is going to have the general shape that's shown here in these plots. So this is how much flux the stars are emitting over different wavelengths. So the black line indicates an SED for an O star at 40,000 Kelvin, and the blue is a B star at 25,000 Kelvin. And so what's important to note here is the shape of the SED, and also that it peaks in the ultraviolet wavelengths, so very short wavelengths. And this is because they are such luminous objects. They put out so much energy, so a lot of their energy is put out in these very short wavelengths. So one important thing to note is this red dotted line that I've put here. This is the Lyman limit, which occurs at 912 angstroms. And this is the wavelength which will ionize hydrogen from the ground state. So all light that is emitted by these stars below this wavelength limit will be absorbed by interstellar gas. So we can't observe beyond that limit. And you can see this is a problem for O and B stars because a good amount of their flux is still occurring past this limit. So we have to rely on models to estimate what the flux will look like beyond that limit because we can't directly observe it. So O and B stars are the main source of ultraviolet radiation for spiral galaxies, and they power far infrared luminosity through the heating of dust. So whenever you see a nice pretty picture of a spiral galaxy like this one, all these bright stars in the spiral arms are these massive O and B stars. They're also progenitors of a lot of really interesting objects like black holes, neutron stars, supernovae, and also LBVs, which are luminous blue variables. These are massive evolved stars that are very variable in their brightness. And the Wolf-Rayet stars, which is also another type of massive evolved star that has lost all of its outer hydrogen. So they are the progenitors of a lot of really interesting objects. So the structure of a B star, or O and B stars, will vary a lot from less massive stars. So there's two modes of energy transport that stars can use to get the energy that they create in the core, from the fusion in the core, to the surface of the star. They use convection or radiation. So less massive stars like M and K, spectral type stars, will be mostly convective, so they'll use convection to transport the energy from the core to the surface. However, as you move to more and more massive stars, you get bigger and bigger radiative zones until you get to massive O and B stars, which are going to be mostly radiative and have a small convective core. So that's going to be the structure of a O and B star. So you end up with what we call a radiative envelope with a convective core at the center. Because they are have higher temperatures in their cores than less massive stars, their energy production is dominated by the CNO cycle instead of the proton-proton chain. So CNO cycle uses carbon, nitrogen, and oxygen atoms as a catalyst to fuse hydrogen atoms into helium. And throughout that process also produces some energy that the star uses to counteract the force of gravity. So less massive stars will exclusively use the proton-proton chain to accomplish this fusion, but as the temperatures in the core start to increase with more massive stars, the energy production is dominated by the CNO cycle. And this means that the stars will burn through their fuel much more quickly than less massive stars. So our sample in particular, which O and B stars we looked at, we had 6 O-type stars and 25 B-type stars that we observed. They ranged in spectral type from O7.5 to B9.5. We had all luminosity classes represented with supergiants, giants, and dwarfs, our main sequence stars. And then 3 of our B stars were members of the Pleiades clusters as well, so it's interesting to note. They have a distance range of the closest at around 30 parsecs, and then our farthest is a B star, a B supergiant, at about 1,000 parsecs. They range in magnitude from about 1 to 5. They have to be fairly bright objects to observe with an interferometer. They range from about 0.2 milliarc seconds to 1.1 milliarc seconds. Of course, our smallest star, as Doug said, is 0.12 milliarc seconds. And we chose particularly the B stars with Hipparcos parallax errors under 10% to keep the errors due to distance down when we calculated our linear radii. So the goals that we wanted to do with this sample was to get fundamental parameters like temperature and radius for these stars that were either model independent or less model dependent than what we have right now. Massive stars are very hard to observe. They tend to be very, very far away. They're also very bright. So if you're trying to get something like an absolute magnitude measurement, you have saturation effects that are causing problems. And so a lot of these estimates that we have right now for radius, temperature, and then, of course, mass and age depend a lot on models. So we want to get observationally determined parameters and use this to test the models and make sure they're predicting accurately the parameters. So the idea is this is similar to the HR diagram I showed at the beginning, but this time we have evolutionary tracks plotted instead of just pictures of stars. So we have temperature on the horizontal axis and luminosity on the vertical axis. And then the different lines represent different evolutionary tracks that the stars can follow depending on what their initial mass is once they move off the main sequence and become a giant and then a supergiant. So where the star falls on this plot will depend on its temperature and then on its luminosity. Well, now luminosity depends on radius and temperature. So of course radius depends, we can get radius from our angular size measurement. So if we can get accurate measurements of angular size and then use that to get an accurate estimate of temperature, we can place our stars on an observational HR diagram with much less dependence on models than what we have right now. So a kind of breakdown of the kind of 2-pronged attack that we used. So we used interferometry to measure angular sizes of stars. So that's the basis of what we did. We used the interferometry to measure the angular size, and then we could combine that with a known distance to calculate the actual physical stellar radius of the star. We can also combine our angular size with integrated flux. So this is another thing we can observe for the star, how much flux or how much energy is it outputting. We can observe this and combine it with our angular size to calculate an effective temperature estimate. So this was our spectrophotometry side of things. So if we have the observed flux that we can observe with the star, we observe the angular size, that's theta, and then we can then calculate an effective temperature estimate. So this is an estimate that will be based on observational parameters instead of models. So in order to do this, we have to use the Char array. For O and B stars, they have very, very small angular diameters. So the angular resolution is only possible with the CHAR array, with the baselines and the wavelength range available. So we have a nice map of the CHAR array that many of you have seen before, of course. So the CHAR array is made up of 6 1-meter telescopes in a Y configuration on Mount Wilson in California. So all of these telescopes are connected by vacuum tubes or light pipes that send the light from the telescope, each telescope, to a central beam combining lab where the light from the telescopes is combined and all the magic happens and we can make our interferometric 2012 to June 2017, so 5 of my nights were lost due to weather and technical. So a little bit basics of interferometry, since that is the basis of what I used. So the idea is to start off very simply. We have 2 telescopes shown here, and they're both looking at the same star. Now, because these telescopes are not physically at the same position, they are separated in distance by some baseline b. The light path that each telescope from the star will be different because these telescopes are. Our interferometric measurements is we want to get constructive interference fringes that we can measure and get visibility measurements from, and ultimately same phase. And the easiest way to get these 2 lights in this. So that's what is happening here. We have optical path length compensation, several reflections to a little bit longer distance before it is combined here, so that when they are combined, the 2 light waves have traveled the same distance up and down to micron accuracy and create a constructive interference fringe that we can observe. So we get 2 observables from interferometric measurements, visibility and closure phase. Closure phase I didn't use for my research, and so I'm not going to go into detail about that. However, it's useful for imagery construction and looking for asymmetry in objects like a companion or a disk around a star, things like that. Visibility is the other observable, and it will tell you about the angular size of the star, which is, of course, what I was interested in. So we have a picture here of a kind of an idealized interference fringe. So this is what an idealized version of the data you would get out from your interferometer. And it has some maximum intensity it reaches and some minimum intensity. So we can take this contrast between the maximum and the minimum. So the contrast here, maximum minus minimum, divided by the sum. And this is going to be an estimate for the visibility, what we call the visibility. So smaller objects will have higher visibilities, and the largest of this visibility estimate could get is 1. Anything greater than 1 does not have a physical meaning. So visibility can only go up to 1. So smaller objects will have higher visibilities, and then larger objects will have lower or smaller visibilities. So there will be less contrast between the maximum and the minimum for a larger star. And so that can be seen in this plot down here. So this is what we could do is make a lot of visibility measurements for our star and then plot them versus baseline. Or often, instead of baseline, here we have spatial frequency, which is baseline divided by wavelength. So either way, you can plot the data that way. And look at visibility curves that will fit the visibility measurements. And you can see for a smaller star, the visibility curve drops off slower and reaches 0 than the larger star. So the larger star drops off quicker and then reaches 0. So the shape of the visibility curve, or how quickly it drops off, can tell us about the size of the star. Also, you could see you could have these secondary lobes structure that occurs in the visibility curve. Of particular interest is this second lobe right here. If you have a star that's sufficiently large enough, or you have sufficiently good enough resolution, you can get data in that lobe, and that will tell you about the limb darkening effects of a star. Limb darkening occurs because stars are not uniformly lit disks. They are balls of gas. So when you look to the edge or limb of a star, you're looking through less gas, so it's less bright than if you were looking right to the center of a star. So this is going to affect affect the size that you measure for your star. So that's something that you want to take into account, and you can actually get information about the limb darkening of the star if you are able to get data in the slope. Generally, resolution of an interferometer is given as wavelength divided by 2 times the baseline. So you can move to smaller and smaller wavelengths, like moving from infrared to optical, and get better resolution. So you can look at smaller objects if you're in the optical wavelengths than in the infrared wavelengths. And then if you increase baseline, so if you make the baseline larger and larger, you can achieve better resolution. So the more spread out the telescopes are, the smaller objects that you can look at. And so that's why it's really important for me to use the largest baselines that Chara had to offer. In general, our observations are conducted in what's called brackets, which are a sequence of 3 scans. We look at a calibrator star first, then the target star, and then we go back to a calibrator star. And so this allows us to calibrate the visibilities that we measure due to instrumental effects. So just to give a perspective, and Doug kind of in his introduction gave a good example too of Frisbee on the moon, but just to give a perspective of how small objects we are looking at. So I'm dealing with stars on the order of 0.5 milliarcseconds. Now 1 arcsecond is 1/36,000th of a degree, and it's equivalent to, if you were looking at a dime, 2.3 miles. You could resolve how big a disk is at 2.3 miles away. And that's 1 arcsecond. A milliarcsecond is 1,000th of an arcsecond. So I'm dealing with very, very small sizes. And then for reference, we have a supergiant star, Betelgeuse, as seen from Earth, is about 55 milliarcseconds. And so again, I'm dealing with 0.5 milliarcsecond scale. So another important thing to take into account for our visibility curves are binary stars. It is very common for O and B stars to be in binary or multiple star systems. So this is something that we had to account for. We couldn't just ignore. There's 2 effects that a binary star or a companion to your star can have on the visibility curve. First, if it's not too close, but close enough to affect it a little bit, it can just add incoherent flux to the visibility curve. So what that will do is we'll just overall lower all of your visibilities. So if you do not correct for this effect, you'll fit the visibilities and it will look like your star is larger than it actually is because you have lower visibilities. So if you correct for it, then you raise your visibilities back up to a higher point and the star appears smaller. So this is due to incoherent flux from the companion. Now, if the companion is even closer, it can do more than just add incoherent flux. It can actually cause a modulation, a periodic modulation in the visibility curve. So instead of just having a visibility curve that looks like this, we could have something that looks like this, where we have this periodic modulation. Now, the separation between the peaks and the modulation will tell you about the binary separation, and the minimum visibility that the curve gets to will tell you about the flux ratio between the 2 stars. So these are the 2 effects that we have to be careful to account for our massive stars. So I want to say a little bit about calibrators because they are very important for interferometric measurements, and they're even more important for our stars in particular because they're so small. So an ideal calibrator is first smaller than the target and ideally unresolved. And the idea here is that an unresolved target will have a visibility of 1, regardless of what its actual angular size is. So if your calibrator is unresolved, then you can neglect, or it has less effect, the errors due to your assumed size of the calibrator. So now this is ideal, but you can't always meet this requirement. You also want the calibrator to be similar in magnitude to the target, and you want the calibrator to be close to the target in the sky, so you're dealing with similar atmospheric conditions between the calibrator and the target. So for our O and B stars, it was very difficult to meet all these conditions for our calibrators because the O and B stars are already very small. So finding a calibrator that is smaller than the target but still bright enough to be a similar magnitude, it was sometimes difficult to do. Because of that, some of our calibrators that we used were in fact larger than our target stars. And in this case, they can still be used as calibrators. We just have to be very careful with looking at the errors, including in our error budget, the assumed calibrator size and the uncertainty in the calibrator size. So I used two beam combiners at Chara to do my observations. I used the CLIMB beam combiner for the larger stars. CLIMB stands for Classic Interferometry with Multiple Baselines. I observed 8 stars with CLIMB, and it has about a 0.5 millisecond resolution operating in the H-band, which is where I observed. It can use also do K-band measurements. And then for my smaller stars, I used the PAVO beam combiner, which stands for Precision Astronomical Visible Observations. We had 27 stars observed with that beam combiner and has about a 0.2 millisecond resolution. It operates in the R band, so shorter wavelength range than CLIMB, which is why we can get better resolution with PAVO. There were 4 stars that overlapped and were observed with both PAVO and CLIMB, and we could compare the measurements from the two instruments, which I'll talk about a little bit later in the talk. So a little bit about the CLIMB beam combiner. It's an open-air aperture plane beam combiner, and it uses 3 telescopes at once. And this is just an example of all the GUIs involved with running the array and running the CLIMB instrument itself. And it's an example of some actual data that you would get from the CLIMB beam. So these are the fringes. I was kind of showing you an idealized picture of a fringe earlier. This is what we actually see in the data. This is also called a waterfall plot. So all these bright points are the fringes. And the idea is we want to track them so that they stay near the center of the plot as we go through time. You'll get 3 visibility points per observation, per 1 bracket with CLIMB, and 1 closure phase measurement. The PAVO beam combiner is a little bit different from CLIMB. It's a spectrally dispersed pupil plane beam combiner. It can use 3 telescopes, but currently the data analysis is not well understood for 3 telescopes, so we used it in 2 telescope mode. Again, this is an example of the data that you get from PAVO. So these are the fringes that we spent all night looking for, hoping to see, and hoping to keep. So I probably spent 80% of my observing time just staring at this little window. And this is an example of aligning the camera for PAVO on the pupil plane. So because PAVO is a little bit different than CLIMB, it is spectrally dispersed, so it uses a prism to disperse the fringes into independent spectral channels. So because of that, you'll get 23 visibility points per observation instead of 3 that you get per observation that you get with CLIMB. However, since we're only using 2 telescopes, we do not get a closer phase measurement. You need at least 3 telescopes to get a closer phase. So because we were using 2 different beam combiners with PAVO and CLIMB, we wanted to have a fitting routine that uniformly fit all of our data instead of using 2 different pipelines for the data. So all the data from both combiners was fit with an error-weighted fit for a single star limb darkened disk model. We used the linear limb darkening law, and the limb darkening coefficients were interpolated from Claret et al. 2011. So this is an example of PAVO data on the left for 1 star with error-weighted fit shown in the solid line. And then this is CLIMB data on the right with an error-weighted fit shown in the solid line for a different star. So just to give you an example of what the data from the 2 combiners would look like. So the other half of the project was to do some spectrophotometric modeling to go along with our interferometric measurements. So the idea is we collected observed spectra from several sources and fit the observed spectra with atmospheric models. So we collected the UV data, ultraviolet data from the IUE or from the UV Bright Star Spectrophotometric Catalog. The optical data for most stars was from a catalog by Bernashev, 1985, and then we used infrared photometry points from 2MASS and WISE. However, for stars like the supergiants and giants stars that we had in our sample that have an infrared excess, we did not use the 2MASS and WISE points for the fitting because they would be higher than the rest of the points due to the infrared excess from winds that are common in giants and supergiants. So we then collected the data from all these different sources and fit them with different models depending on the temperature of the star. So for the hotter star O stars, we used T-LUS-D-O star models. For the B stars, T-LUS-D-B star models. And then for the cooler B stars, we used Atlas 9 models. And this is just an example of a fit SED. So you can see the black points. These are the observed data points that we are fitting the model to. So just a quick rundown of the three models that we used. So for the hotter stars, we used the TLSD O and B star models. These are both non-LTE, line-blanketed, plane parallel models, and then their temperature ranges are appropriate for the type of star that they go with. Of course, a hotter temperature range for the O stars than the B stars. One important difference to note is that the O star models do have a larger turbulent velocity of 10 kilometers per second compared to the B stars at 2 kilometers per second. However, some of our B stars were cooler than 15,000 Kelvin, so the TLC B stars only go to 50,000. So for those cooler stars, we use the Atlas 9 models to fit the spectral data. Atlas 9 models are an LTE plane parallel model, so that's one big difference between the Atlas 9 and the TLSD models. It has a very big temperature range. However, we just wanted to use it to overlap our cooler B stars, so our temperature range was just 5,000 to 20,000 Kelvin. And this is just an example graph here comparing the two models. In the gray is the Atlas 9 models, and then the solid black line is the TLSD models. So what we did to fit our models is, to fit a model to our spectral data, we used a grid search method that searched 3 parameters at once. We allowed angular size to vary, limb-darkened angular size, effective temperature, and extinction, EB minus phi. So once we ran through that grid search, what we get out is a chi-squared matrix that results from the best fit EB minus phi as a function of temperature and size. So for each pair of temperature and size, we have a best fit reddening. So we can make these contour plots that's shown here. So these contours are the chi-squared contours that result from the best fit reddening for each pair of temperature and size. So let's plot here. We have size on the x-axis and temperature on the y-axis, and then the chi-squared contours. So this is showing where the model predicts the best fit size and best fit temperature will be based on the spectral data that it fit. Now overplotted, we have a vertical line. This is our interferometric measurement. So this is independent of spectral data or models. This is what we measured with the CHAR array. This is our interferometric measurement for angular size with a 1 sigma error margin. And then the horizontal line is the average literature temperature for the given star with a 1 sigma error margin. So we can compare our measurements to the models and the literature temperature to the models as well. So there's a couple ways that we can interpret these plots and get information from these plots. The first thing we can do is look at our interferometric size and see where it crosses closest to the minimum of the contour, of the chi-squared contour, and from there infer an effective temperature. So this would be the best fit effective temperature that the models, based on the models and our interferometric size. So we can compare so we could get an effective temperature estimate based on our interferometric measurements. Now, another thing we could do, and this is a different star, just to show they don't always go right to the center. Sometimes it doesn't fit quite as well. But we can work backwards, and we can say, well, what temperature does the model finding the minimum at? So the global minimum of the chi-squared. And okay, what angular size does that correspond to? So then we can compare our observed interferometric angular sizes with what the model is predicting the best size will be. And so we can test how well the model is predicting the sizes of the stars. Now, for this star and for a lot of especially my cooler B stars, the temperature is fairly tightly constrained with the contours. However, for the O stars and some of the hotter B stars, we have a contour that looks like this. So we have a kind of a valley of chi-squared minimum instead of a tightly constrained point. So in that case, we can look at the average literature temperature, see where does it cross at the closest to the minimum of the chi-squared contour for the model, and get an effective a angular size estimate from that. So again, we can compare our interferometric measurements to what the model is predicting the best fit for the size will be. So another thing we had to take into account, as I talked about briefly before, was companions. This is very important for massive stars. It's very common for them to be in multiple systems. 15 out of our 31 target stars had a close, bright companion or more than one close, bright companion that we needed to account for in our measurements. So two things we did. For interferometry, the visibilities were corrected for incoherent flux due to the companion. So this was calculated based on the projected separation of the companion, the delta magnitude, and the seeing. And then for our spectrophotometry, the flux of the companion or multiple companions was added to the flux of the target for the model flux. And this calculation was based on the delta magnitude between the two stars and the assumed effective temperature and log G for the companion. So just to give you an idea of why this is important from the interferometric side. So this is representing the field of view of the interferometer. And then we have our target star that we're observing there in the center. So you could have a case like in the center one here where the companion star is not quite close enough to be in the field of view. So there's no extra light being put into our measurements, so we don't need to make it a correction. However, the seeing for the night can affect this. If the seeing is worse, it can make the light blur out over a larger area. So you can have an example here on the left. The companion star is still the same distance away, but because of the worse seeing, the light is blurred out over a larger area, and now some of the light is spilling into the field of view and does affect our measurements. So we need to know the seeing, the average seeing for the night of our observation. And then, of course, separation matters as well. Over here on the right, if your companion is closer, of course, it may be partially or all the way in the field of view, and this is going to affect how much light it contributes to the visibility curve. For interferometric measurements, our field of view is about 1 arcsecond. So similarly, we had to take into account this effect for the spectrophotometry. So this is just an example of two spectra of 20,000 Kelvin star and 15,000 Kelvin star. So this is just an example of, maybe the target star and a companion star. Now, when you collect your observed data, you don't get two nice spectra like this. You get just all the combined light from all the stars. So if you try and fit the observed data with a model, and you don't account for this companion star, it's not going to fit because the observed data is combining the light from all of the stars in the system. So this is an example of an uncorrected corrected fit for one star. This star actually has two close companions. As you can see on the top, it's uncorrected. So this model in the green line, which might be kind of hard to see, is just for one single star. It's just assuming there's no companions. It's just the target star. And you can see it does not fit the data very well. It's too low to fit the observed data. However, if you correct for that, you add in the model spectra for the companions, and now it is fitting much better the observed data. So we have to take those effects into account for both our spectrophotometry and our interferometry. So finally, we get to some results. We can apply all of this and use our comparisons between our observed sizes and models to look at some results. First, we have the O stars. So just to remind you, I observed 6 O stars. And so this plot here is comparing on the x-axis our measured size, so observed size with interferometry, versus what the model says the best fit size is. So we're testing the model, seeing how well the model is doing. And you can see in general, there's a pretty good fit. There's a couple of caveats here. These 4 stars that are in blue are stars where the data is probably affected by, the errors are probably affected by systematic effects. These 3 stars here, these are Xi-Per, Alpha Cam, and Zeta Ori. These stars, we only got 1 bracket of data on one night of observation, and we did see what looked like a bias in the data. We corrected for this bias, but because of that, we take these to be minimum estimates for the size instead of actual determinations of the size. This star up here is Zeta Oph. It's a special star. It's rotationally distorted, and I'll talk about it next. But that could be why it's not fitting the model quite as well because of the rotational effects. Just for reference, this solid line is a line with a slope of 1, and then this dotted line is the best fit line to all the data points. So the two stars that are left that don't have a bias in the data and aren't rotationally distorted are these two stars here. This is Lambda Ori and 10 Lac. And you can see that they fit with the model predictions very well. There's no discrepancy between the two sizes. However, the average temperature that we calculated or derived for these two stars is higher than their average literature temperature by about 1.4 kilokelvin. So Zeta Oph is a really interesting star. As I said before, it's a rapid rotator, very rapid rotator. It has a V-Sine at 348 kilometers per second. It's very close to its critical velocity. And so because of this, it's going to be distorted from a perfect sphere and have an oblate shape. And we were able to observe this distortion. We observed it in two nearly orthogonal baselines and saw different angular sizes. So on one baseline, we measured 0.54 milliarc seconds, and on another, 0.46 milliarc seconds. Now, in the past, this star did have a disk around it, a circumstellar disk. It doesn't currently, but in the past it did. And during that time, a spectropolarimetry study was conducted by Porokit et al., and they got a position angle of 132.5 degrees for the circumstellar disk, which we assume is parallel to the axis of the star. So we can fix that position angle, we set it, and do an ellipse fit to our data to get a fit for the major and minor axes, which is what's shown here. And you can see that they fit very well with our observed parameters for the star. And as I mentioned at the beginning of the talk, Zeta Oph is a runaway star, which puts it in the rare position as being a single O star, as many O stars and B stars are in multiple systems. Another really interesting star that Doug mentioned at the beginning was 10 Lac. We resolved it at 0.12 milliarc seconds, which is below the nominal resolution limit of Pavo at 0.2 milliarc seconds. Correct me if I'm mistaken, anyone, but I believe this is the smallest star ever resolved with the Char array. So I just wanted to show the visibility curve because it was so small. Of course, there's quite a bit of uncertainty in the visibility measurements, but you can see the visibility curve starting to come down, showing that we've at least partially resolved the star. It does fit very well with the models. So this is the contour map for 10 Lac and the SED fit as well. So you can see it's agreeing very well with what the model is predicting for the size and the temperature and the average literature temperature as well. What's interesting is both the average literature temperature and our interferometrically determined temperature was about 36 kilokelvin. And this is higher than its spectral type of 09, which should be about 32 kilokelvin. It's interesting because 10 Lac is actually used as a standard for the 09 spectral type. So there might be an issue here with it's showing a much higher temperature than the spectral type it's associated with. So we can make the same kind of comparisons with our B stars. So we have our B star results. We have 25 B stars. So similar to those stars on the left here, we have a plot showing our observed size versus what the model predicts the best size should be based on the spectral data. We've got the solid line is a line with a slope of 1. Dotted line is the best fit to the data. And then on the right, we have the temperatures in comparison. So this is our derived effective temperature estimate compared to the average literature effective temperature estimate. So what it appears from a couple things from looking at these graphs. The first, just looking at the ratio here of model to observed, it looks like the model is overestimating the angular diameters by about 4%. Also, we have the temperatures being underestimated by the literature by about 7%. And this makes sense because size and temperature are related with the flux of the star. If one goes up, the other must go down in order for flux to be conserved. Now, a kind of interesting feature in this plot is that the larger stars seem to be agreeing with the model better, and then the overestimation really starts to come into effect here with the smaller stars. Now, these larger stars were observed with CLIMB, whereas these smaller stars were observed with PAVO. The different symbols, the squares are stars that were fit with the T-Lusty models. The triangles were stars fit with the Atlas 9 models, and the filled triangles are stars with CLIMB data or CLIMB and PAVO data for some of the smaller ones. So And there is some discrepancy we found between the CLIME and the Pavo beam combiners, which I'll talk about next. So this is just a comparison of the stars that we were able to observe with both beam combiners, Pavo and CLIME. Now I said before we observed 4 stars with both beam combiners, but we only used 3 for the comparison here. So we have, and this top star is just, I observed it with the H and K band with CLIME, so that's why it's included here. But really we're looking at these bottom 3 stars. And so to investigate this comparison, we fit the CLIME data ran the CLIME data through 3 different data reduction pipelines. First, we just used the standard CLIME data reduction pipeline, so that's the CLIME H-band column. We used the WM CLIME stands for weighted mean CLIME, so that's using the standard CLIME pipeline, but using a weighted mean to combine the power spectra instead of just an average. And then JDM is a data reduction CLIME pipeline, independent pipeline written by Jean Manier to reduce CLIME data. So if you look at all of these sizes, there is some variation between the sizes, but there is no systematic effect, and they agree with each other within errors. However, there is a systematic effect between the Pavo sizes and the CLIME sizes. The Pavo sizes are consistently smaller than the CLIME sizes, and the effect gets worse for smaller stars. And so these 2 stars that I've highlighted are the 2 stars where the discrepancy is the worst. And this star in particular, HG 196867, has a very big discrepancy of almost 5 sigma. However, it is a binary star with a fairly close companion. We did correct for an incoherent flux for this companion for both the Pavo and the CLIME observations, but it could be that this binary or even a second unknown companion is affecting the measurements, and that's why we're seeing such a big discrepancy. The other star, 2149238, as far as we know, is a single star, and we're still seeing this discrepancy with smaller sizes for Pavo than measured with CLIME. Pavo because it's operating at a short wavelength, it has better resolution. Pavo will be sampling farther down on the visibility curve for a given star, so it will give a better constraint, a more strict constraint on the size of the star due to that fact. So with this, seeing this discrepancy, we suggest that Pavo sizes will give more accurate results for stars smaller than 0.8 milliarc seconds. So as you can see, this last star that we compared, 218045, it's still kind of following the trend. This Pavo size is smaller, but it's a very small difference, and the 2 sizes agree with an error. So as you get to larger stars, it appears this discrepancy is not as bad. Of course, we need a much bigger sample size than this to really investigate this issue. This is only 3 stars, so to really investigate the issue between Pavo and CLIME, we need a dedicated observing program with a lot of stars to see what's happening. So 55 Sig was one of my really interesting B stars. It's the only B supergiant star in my sample. I have 2 O supergiants and 1 B supergiant. So we measured an angular diameter for it of 0.448 milliarc seconds and a best fit effective temperature of 18.8 kilokelvin. However, as you look at the contour and the SED shown on the right here, it doesn't fit the model very well. It's our observed interferometric size is not going through the center or near the center of the contour, and again, the green line is a little hard to see, but it's lower than the observed point, so it's not really fitting the visibility or the observed data very well. But one thing to note is that both the models that we use, the TLSD and the Atlas 9 models, do not take into account stellar wind effects. And now stellar winds can be very important for supergiant stars. They can have very strong stellar winds. So in 2015, a study was done by Cross et al., which modeled spectra that they observed for the star with the fast wind code, which does account for the structure of stellar winds. From their modeling, they find a best fit effective temperature of 18.8 kilokelvin, and they find a stellar radius of 57 solar radii. When combined with our assumed distance from the Gaia DR2, we get an angular size of 0.5 milliarc seconds, which fits both the temperature and the size fit very well with our observed parameters. So it could be that what we're seeing here is that models that do not take into account effects of stellar winds will not do a good job fitting supergiant B stars. Another interesting B star in my sample was Markab. This is, for us, a very large star, one of our largest stars at 1.052 milliarc seconds. And we observed this star with both PAVO and CLIMB beam combiner. This is PAVO data. And because the star is so large and PAVO has such small resolution, we were able to get data in the second lobe. And so you can see from the visibility curve here, we have data in the first lobe very nicely constraining the size of the star. And then we have our second lobe data. So here we have a zoomed in look at the second lobe data. This solid line is a limb darkened fit with a limb darkening coefficient of 0.34. And the dashed line is a fit with no limb darkening. Now at first look at the data, it looks like it's not matching the limb darkened fit very well. It looks like we need a smaller limb darkening coefficient or perhaps no limb darkening to really fit this data well. However, if we break it down and look at it bracket by bracket, we see a little bit different picture. So this is kind of like a time series starting here and moving left to right. So you can see at the beginning of the night, the data does seem to fit the limb darkened fit fairly well. However, as we move on, it appears that observing conditions degraded and we get much larger errors in our visibility as well as larger visibility measurements. Now, these measurements are very difficult to make. These are very, very small visibilities that we're measuring in the second lobe. So if you do not have ideal observing conditions, it can be very difficult to get accurate measurements for this second lobe data. So I can put everything together, all of my O and B star observations, and compare our interferometric observations to some interferometric observations that were made in the past. So we have squares are Vega observations by Shalouf in 2014. We have these are two O stars observed by Hambre-Brown in 1974 by the Narby stellar intensity interferometer. So those are these two circles right here. And these are the only interferometric measurements of O stars until my measurements. And then we also have some PAVO observations by White and by Maestro et al. Shown in the triangles. So this is showing that our measurements agree well with previous interferometric measurements. One thing of note, this one is the worst fitting star. This star was observed with CLIMB. The rest were PAVO. So the last thing we can do is what we wanted to do at the beginning was place our stars on an observational HR diagram. So again, this is like the HR diagram that we showed at the beginning. We've got temperature increasing on the horizontal axis, and then this time we have, instead of luminosity, a lot of radius on the vertical axis. So the pink diamonds are the B stars, the blue points are the O stars, with the dark blue triangles being the 3 O stars that we only have upper limits for the temperatures for, instead of really tightly constrained estimates. So a couple interesting stars, we've got our 3 supergiants, so our 2 O supergiants, Theta Orion Alpha Cam, and then our B supergiant up here, 55 Sig. And this area circled in green is around where our 3 Pleiades members would be. So with this type of diagram, we can begin to get estimates for things like mass and age for these stars. So we have evolutionary tracks for different initial masses shown here in the solid lines, and then some isochrones shown here in the dashed lines, and these are from the MESA grid. So we can begin to use these evolutionary tracks and isochrones to estimate mass and age for our massive stars. So just to remind everyone what I did, I got interferometric angular diameters for 31 O and B stars, fit the observed spectra with atmospheric models, and got observationally determined radii and temperatures that I could then compare with model predictions. From that work, we conclude that PAVO diameters will be more accurate than CLIMB for stars smaller than 0.8 milliarc seconds. Models without stellar winds may be insufficient for supergiants, and the effective temperature scale for massive stars may need to be revised. We found that pretty much all of our O and B stars had hotter effective temperature estimates that we measured when compared to literature estimates. Any questions?